Okay, notes 10.12, Lagrange error bound. So Lagrange error bound is going to be going off the the alternate series error bound that we did in a previous notes. So starting off with that definition, remember we said the exact value is the approximate value plus the remainder. Okay, and our goal is to try to get as close to the exact value as possible, which means that our error should be very, very small. So recall that this formula is f of x is equal to p of x plus r of x, where p of x is the approximate and r of x is the remainder. So if we solve for r of x, we get r of x is equal to f of x minus p of x, which means the error is going to be the absolute value of r sub n of x, which is going to be equal to the absolute value of f of x minus p sub n of x. Okay, so recall that, let's say we're using the Taylor polynomial. So this whole part here is representing the Taylor polynomial. This is our approximation to the actual function f of x. And so if we want to find the actual function, we would take our approximation and we would add it to r of x. So remember, this is our remainder. Okay, so another way to look at this is that our remainder is going to be the n plus 1 derivative. So we would write that as f derivative n plus 1 of c times x minus c to the power of n plus 1 over n plus 1 factorial. Okay. However, if we are trying to estimate the remainder, it's not always going to be that next derivative in the Taylor polynomial. What we need to try to find is the maximum value of this part here. So the maximum value. Well, in order to find the maximum value of this, we need to see what the remainder is and how far the whole function can go. So looking at the upper bound of the entire function is going to give us the maximum value of our remainder, which is going to help add to our approximation and find our original function. So when we do this, we can't use c anymore because c is our approximation. So we're going to let c be z. Okay, so I'm changing my variable there to not confuse it with c, which is my center. Okay, so that means this right here means my remainder at most has to be this value. So at most will equal the following. Okay, the maximum value of that. And so that leads us to the definition of a Lagrange error bound. It says let f be differentiable. Okay, makes sense. We got to do the derivatives for the Taylor polynomials through the order n plus 1, which means we're looking at the next derivative above. The error between the Taylor polynomial and f of x is bounded by this remainder, absolute value of the remainder function, which is our error. So this gives us that we have to have the absolute value of the maximum of f n plus 1 derivative of z times x minus c to the power of n plus 1 all over n plus 1 factorial. And then notice right here it says where z is some number between c and x. So when we're writing this interval, z is going to be between c and x. And so we always need to make sure we check that interval when we're trying to find the maximum value of this that would give us the closest remainder to help us find the actual function. So let's look at an example. Okay, so number 1 says the fourth degree of the Maclaurin polynomial. Remember, Maclaurin polynomial is when x is equal to 0. for cosine of x is given by the following. So p sub 4 of x, and here is our approximation. You should notice that this approximation is a Taylor polynomial, okay? And since we're using a Maclaurin polynomial, the only difference is that the center is around x equals 0. If this polynomial is used to approximate cosine of 0.2, what is the Lagrange error bound? And so the first thing we need to do is we need to write that, okay, cosine of 0.2 is being approximated by p sub 4 of 0.2. And if I was just to plug this into the Taylor polynomial that was given, then I would get 0.980067. Again, this is an approximation. Okay. And so using my Lagrange error bound formula, I know that r, this is the fourth degree, so sub 4 of x has to be less than or equal to the maximum of, and we're going to leave this blank for now, okay? Just know that this blank is going to be the fifth derivative of cosine of x, okay? Times x minus c, x minus c, so that's 0.2, the value we're trying to find, minus c, which is our center around x equals 0, to the power of n plus 1, so 4 plus 1, all over 4 plus 1 factorial. Okay. So what we need to do now is we need to find the fifth derivative of cosine. So off to the side, I'm going to do, okay, my original function is cosine of x. My first derivative is negative sine of x. Second derivative is negative cosine of x. Third derivative is sine of x. Fourth derivative is cosine of x. And then fifth derivative is negative sine of x. So that's what I'm going to write here, negative sine of z. Because remember, this is always z, not to get it confused with the other variables in this problem. Okay? Remember that z needs to be between c and x. So it needs to be between 0 and 0.2. Okay. However, and I'm going to emphasize this, on the AP exam, they don't care that you follow this exact interval. They care if you know what the bounds are for the function that we're plugging in, the maximum of that function. Well, since our function is sine, we know that the maximum of cosine or sine, let's say the max for cosine of x and sine of x, is going to be 1. Okay, which means it's not going to get any larger than this bound, because remember, sine and cosine are a oscillating function. It's going to go up, down, so the maximum always 1, minimum always negative 1, and then repeating. Okay, so because of this, we don't really care about the interval where z is here. We know that no matter what z value we plug in for negative sine, our maximum value is only going to get to 1. And so what we're assuming here is that this value here is just 1. So when I rewrite this, I have r sub 4 of x is less than or equal to the absolute value. Well, the maximum of the fifth derivative can only be up to 1. So I'm going to put 1 times 0.2 to the fifth power over 5 factorial. If I put that into the calculator, I'm going to get a very, 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 very small decimal. So I'm just going to write it as 2.667 times 10 to the negative 6 power, which is, again, a very, very small number. And so this, what we just found, is our error bound. This is how far off our approximation is to the exact value. So how far our approximation is to the exact value. Okay, which means 0.980067, that approximation, the actual value of cosine of 0.2 is going to just be off by 0.0000026667, which is very, very good. That means our error is very small, which means this Maclaurin polynomial is a great approximation for cosine of 0.2. Okay, so this right here would be our answer. Okay, so let's look at number 2. Number 2 says use a third degree Taylor polynomial on the interval 0 to 1 for e to the x centered about x equals 0 to approximate e to the first power. What is the error bound of this approximation? Okay, well, e to the first power, okay, is going to be approximated by the third degree Taylor polynomial. So p sub 3 of 1. And we have to know the definition of a Taylor polynomial in order to do this quickly, okay, or by memory. And so I know this is 1 plus 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial, which gives us 2.667, okay, which means e to the first power is approximated by a third degree Taylor polynomial to be about 2.667. That is our approximate value. Okay, so we found these values because I know that my function e to the x, no matter how many times I take the derivative, is still going to be e to the x. Okay, which means if I plug in 0 for x, I'm going to get 1. No matter what my derivative is, I'm still going to get 1. So that's how I was able to write this third degree Taylor polynomial. So now going back to the Lagrange error bound, I'm going to do r sub 3 of x is less than or equal to the maximum of, and then again, since my derivative doesn't change, that means I'm not really finding my n plus 1 derivative. It's just the exact same, which is e to the x. But to not confuse it, I'm going to write e to the z. Remember, I'm using that z in place of x or c to not confuse it with anything else. Okay, then I'm just filling in the rest of my definition. So I have 1 minus 0 to the power of 3 plus 1 over 3 plus 1 factorial. Okay, and from here, again, I know that, okay, right here, this z has to be between c and x. So this is going to be between 0 and z and then 1. So z is between 0 and 1. Okay, however, if I look at either of those bounds, if I look at 0, if I look at 1, if I plug in 1 for z, that's going to give me my maximum value. So I'm just going to use e to the first power for this maximum f to the n plus 1 derivative to say that no matter what, that's the biggest number that I'm going to be able to get. So I'm just going to plug in 1 to get my maximum value. And so I get that this is less than or equal to the absolute value of e to the first power times 1 over 4 factorial, which gives me 0.1132617. Okay, that is my answer, which means that this third degree Taylor polynomial approximation of 2.667 can vary based off of the error of 0.113267. So that means it could be a value 0.1132 larger or 0.1132 smaller. Okay, let's look at one more example. This one says, what is the smallest order Taylor polynomial centered at x equals 1, which will approximate e to the power of x minus 1 on the interval 0 to 3 with a Lagrange error bound less than 1? So first I need to write out my Taylor polynomial, and I can't write which order this is going to be because that's what I'm trying to find. So just in general, I know that p of x is 1 plus x minus 1 plus x minus 1 squared over 2 factorial plus x minus 1 cubed over 3 factorial, etc. It goes on and on forever. Okay. And again, I know it's always going to be this one value here because again, if I look at my function, my function is e to the power of x minus 1, which means the first derivative of that is looking at the derivative of the exponent, which is always going to be 1. So that means this function's derivative is going to remain the same, which means if I plug in 1, because that's my centered around, it's centered around x equals 1. 1 minus 1 is 0, e to the 0 is 1 for every single one of these. So that means that f of 1 equals 1 all the way to f nth derivative of 1 equals 1. So that's how I was able to write my Taylor polynomial. So from here, doing my formula for Lagrange error bound, I get r sub n of x has to be less than or equal to the maximum. And then again, I know this has to be n plus 1. So f n plus 1 derivative of z times x minus 1 to the power of n plus 1 all over n plus 1 factorial. And it says the error bound has to be less than 1. So I'm going to write less than 1. Okay. So again, I know that this here, no matter how many derivatives I take, is always going to be e to the x minus 1. And my z has to be between c and x. So that's going to be 0, less than z, less than 3. Well, in order to find the maximum value on that interval, that would be me saying, well, let's plug in 3. That's the highest z can go to. So if I plug in 3, I'm left with e to the power of 3 minus 1, which is e squared. So I'm going to plug in e squared as my maximum function. So then I am left with the absolute value of this entire thing, but just remember absolute value is going to keep it positive, and e squared is already positive, so I can technically just drop it. And so I have e squared times, and if I'm plugging in 3 for, if I'm plugging in 3, that means I'm also going to plug in 3 for x, because x is that upper bound that I'm using here. So this value is also going to be 3. So then I have 3 minus 1 to the power of n plus 1 over n plus 1 factorial has to be less than 1. So from here, you're going to go to Desmos, and I'm going to open it up in just a moment. And on Desmos, what you're going to do is you're going to just type in this part. When you type in this part on Desmos, it's going to ask you if you want to add a slider for n. You're going to say yes. So you're going to add a slider for n. And what we're trying to do is we're trying to see how big does our n value have to be in order for this remainder, this error, to still be less than 1. And so we're going to slowly increase it. So n equals 1, n equals 2, etc. until we find a value that is less than 1. Okay, so let's go ahead and open up Desmos. Sorry, I'm trying to put both up here. Let me try that one more time. There we go. Okay, so on Desmos, I'm just typing in the part that I circled. So this is e squared times 3 minus 1 to the power of n plus 1. Just make sure to put that in parentheses. Okay, and then I want this whole thing to be divided by n plus 1 factorial. And then this whole thing is less than 1. Okay, so notice as soon as I type this in, it says add slider for n. I'm going to click on that. And then before I start moving this around, I want to click on this so it can help me adjust the settings. So we want to start when n is 1. Okay, and then we can go up to as many n values as we want. So let's just start 1 through 10 and see if we can find a value that's less than 1. The step here, I want my n value, since we're talking about derivatives, to be a whole number. So I'm going to say my step is 1. And so when I click that, notice that every single time, one second, we got to get rid of this part here. So there we go. You see how it shows me my values now? Okay, so at n equals 1, I have 14.7. That is not less than 1. So I check n equals 2. 9.85, not less than 1. N equals 3, 4.9, which is not less than 1. Okay, 4, it's getting closer. Now it's 1.97, still not less than 1. But at n equals 5, I get 0.65, okay, etc., which means this value is less than 1, which means I need to do 5 derivatives, which means my answer to find what is the smallest order Taylor polynomial is going to be a 5th order Taylor polynomial, and that's going to be my answer.